So I hope that you have answered all the 10 questions within 15 minutes. This is the part 19 of ISRO mock test series for technical assistant examinations for various locations. So I hope that you have seen all the questions. Now let us see the solutions one by one. The first question is, conductance is expressed in terms of dash. That is, the question is asking the unit of conductance. A, MHO, that is mho. B, MHO per meter. C, ohm per meter. D, meter per ohm. So, conductance is equal to 1 by resistance, right? So, the unit of resistance is equal to ohm. And if you reverse it, it will be MHO. And this is the unit of conductance. Okay. So, the correct answer here is option A, MHO. This is the unit of conductance. Correct answer for first question is option A. Moving on to the second question. You can see the questions while discussing the solutions. Okay. Second question is, in a current voltage relationship graph of a linear resistance, the slope of the graph will indicate dash. So this graph is indicating current voltage relationship, not voltage current relationship. Okay. So what is the slope of graph indicating? So it will be, the slope of the graph will be current by voltage, right? So it is a current to voltage graph. So the slope will be equal to the ratio of current to voltage, right? So the ratio of current to voltage is nothing but conductance. Again, this question is regarding the conductance. Okay. So if the question was in a voltage to current relationship graph, then the slope is resistance. Okay. So if it is current to voltage graph, means current by voltage will be your slope, and that is equal to conductance. And if the graph is voltage to current, means the slope will give the resistance, which is 1 by conductance. Okay. Here the options are A, conductance, B, resistance, C, resistivity, D, a constant. Correct answer is A, conductance. Okay. So that is the correct answer for your second question. Now moving on to the third question. So the third question is from network analysis. You need to perform actually star to delta conversion. Okay, so let's read the question. Find the equivalent resistance between node 1 and node 3. You'll be seeing the figure. Anyway, I'm drawing it for you. This is 3, this is 1, this is 2. The resistances are, this is 11, this is 10, this is 10, right? Now you need to find the equivalent between these two nodes. This is node 1 and this is node 3. What is the resistance equivalent between node 1 and node 3 in the star network shown? So this network, which is the underlying network, is a star network, right? And you can form a delta out of this. Okay, so the inner one is a star one. The outer one is called the delta, right? Now how to form the delta from the star? That is called star to delta conversion. Okay, star to delta conversion. So I was receiving a request to do how to perform star to delta conversion video. So I'm including that question in this mock test series. So if you want to convert star to delta, the procedure is, see, if you want to, so we are going to take the equivalent between 1 and 3, means we need to find the resistance in this branch of the corresponding delta, right? So you can call this one as R1, this is R2, this is R3. So this R1, R2 and R3 will form the delta connection, and the inner 10 ohm, 11 ohm and 10 ohm forms the star connection. And you can form a delta using R1, R2 and R3 from the inner star. So that is called star to delta conversion. And what will be the value for R1? I'll write R1 will be equal to, take the product of all these combinations, that is 10 into 11 plus 11 into 10 plus 10 into 10, then divided by the opposite resistance. So this branch we need to find the R1 or the resistance. What is the resistance in the opposite branch? It is nothing but 10. Okay. So if you want to have a more clarity, I'll redraw the figure for you. Now this looks little bit simpler, right? In order to understand this, I've just redrawn, no change in connection or anything. Okay, so this is again 10. Now you can find which is the opposite resistance very easily. I've just pulled this little bit down or bend this one. Okay, so in order to find R1, I'm going to write the equation. R1 is equal to 10 into 11 plus 11 into 10 plus 10 into 10 by the opposite one. So this is R1 and the opposite branch is this. For R2, which is the opposite branch, it is this. For R3, which is the opposite branch, it is this 11 ohm, right? Very, very simple, right? So by 10. Now, if you solve it, you will get 110 plus 110 again plus 100 by 10. So that is 320 by 10, which is equal to 32 ohms. So the value for your R1 equal to 32. Now in the question there is no R1, there is no R2 and there is no R3. They are just asking the equivalent resistance between node 1 and node 3. That is nothing but this R1, right? So you have to figure out that this is a star to delta conversion. I hope it is clear. So in order to find R2, same procedure. The numerator is same, only difference is in the opposite resistance. Okay. So for finding R2, you have to take the numerator as same. You have to take the product of all the combinations and take the sum of it. Then divided by the opposite resistance for R2. So here R2, the opposite resistance is 10 again. So it is same. Now for finding R3, numerator is same, denominator will be 11. Okay, I hope it is clear. So then you will get your equivalent delta, which is having R1, R2 and R3. Okay. Anyway, the correct answer for the third question is option C, which is 32. Okay. Moving on to the fourth question. Let me just remove this to make some space. Okay, moving on to the fourth question. For which type of material the number of free electron concentration is equal to the number of donor atoms? Okay, so we know that for making of extrinsic semiconductors, there are two types of extrinsic semiconductors. N type is there and P type is there, right? So N type is obtained by adding of donor impurities, right? So when you are hearing the term donor, then you should know that we are actually meant to, or our idea is to create a N type. This is a general case. And if we are adding acceptor impurity, means our idea is to create P type, right? So the question is, for which type of material the number of free electron concentration is equal to donor atoms? It will be in which case? It will be in N type semiconductor. Very simple question if you know this concept. Okay, correct answer is option C. Moving on to the next question, which is question number 5. Okay, identify the correct condition for a semiconductor to be electrically neutral. Okay, so we are going to talk about the electrical neutrality of a semiconductor, and the various options given are actually combinations of your the donor concentration and the number of electrons and holes created. Okay, so I'll directly write the condition. For a material to be electrically neutral, the concentration of donor impurity, that is ND, plus the number of holes generated, right, that is P, equal to, or the number of holes equal to Na plus number of electrons. Okay, or you can say it is the donor concentration plus hole concentration equal to the acceptor concentration plus electron concentration. So I'll say it once again, the sum of number of donors plus holes is equal to sum of number of acceptors plus electrons. So here donors will generate electrons, right? So electrons will be generated by this donors plus holes equal to Na means acceptors. It will generate what? Holes plus electrons, right? Sorry, N is, we'll write it as electrons. Okay. So, or in simple way, I'll write it as N and P itself. Okay. So, donor atoms creates electrons. Electrons represented using N. Then plus holes is equal to acceptor atoms creates holes plus electrons. Okay. So, then both the else, that is this side and this side of the equation will be equal, and then the material is assumed to be electrically neutral. Okay. So, the correct answer for this question is option A, which is the number of donor atoms plus holes is equal to number of acceptor atoms plus electrons. So, N is a number of electrons, P is a number of holes. Okay, so that you should be knowing. Correct answer for the fifth question is option A. Moving on to the sixth question. Analog data having highest harmonic at 30 kilohertz. Highest harmonic means the maximum frequency or highest harmonic frequency. 30 kilohertz, okay, generated by a sensor has been digitized using 6-level PCM. So here digitizing is done. What will be the rate of digital signal generated? So we are actually going to digitize a signal using a 6-level PCM. So the signal which we are originally using is having a 30 kilohertz highest harmonic, means a peak frequency. So how to understand this question? First, let's see that. Okay, so the peak frequency of your wave is equal to 30 kilohertz, right? And this wave we are going to digitize using PCM, which is having 6 levels. Okay. Now, when we are saying 6 level means we are saying it is getting quantized using 6 levels. So, in order to digitize a signal, we have to perform two things. One is sampling. Second one is quantizing, right? So, we have to perform both these things. Now, the question is, what will be the rate of the digital signal generated? We are not being asked sampling, or we are not being asked quantizing. We need to find what is the rate of the digital signal generated. So, we have to generate a digital signal anyway. So, first we have to sample the signal. Now, while sampling, we have to follow one thing which is called Nyquist criteria. According to Nyquist criteria, the sampling rate or Fs should be greater than or equal to 2 Fm. That is the case, right? So, what will be Fs here? So, we will take equal to. Fs is equal to 2 into 30 kilohertz, which is equal to 60 kilohertz is the rate at which your signal is sampled. Now, next step is to quantize the signal, right? So, in order to perform quantizing, we have to perform 6-level quantizing. And we know that for that quantizing, 2 raised to n greater than or equal to 6. Okay, so it is a 6-level PCM, and for that, here 2 raised to n. Okay, n is the number of bits. Okay, 2 raised to n greater than or equal to 6. So, in that case, n will get as n equal to 3. Right. So, we have the sampling rate as 60 kilohertz and we have the number of bits as 3. Okay. Now, what is the total bit rate? So, the bit rate is Fs into n, NFS. These are actually basics of PCM. We have done video on PCM. Please do watch it. Okay. So, n into Fs. N is 3. 3 into Fs is 60 kilohertz. that is equal to, I'll write it above, okay, 60 into 3, it is 180 kilobits per second. I hope it is clear. So, while discussing a PCM question, you have to discuss or you have to keep two things in mind. One is sampling state, second is quantizing state. In the sampling state, you have to think about the sampling frequency, and while selecting the sampling frequency or the sampling rate, you have to keep Nyquist criteria in mind, which is this. Again, next thing is to find the number of bits with which each sample is quantized. Sorry, each sample is getting digitized. Okay. So, each sample will occupy how many bits? 3 bits. Total samples or sample rate is 60 kilohertz. So, into that will be the total bit rate, right? So, Fs into N, which is 3 into 60 kilohertz, which is 180 kilobits per second. Again, you have to keep this thing in mind. Quantizing level should be, that is 2 raised to n greater than or equal to the quantizing levels, which is 6 level PCM. So, it is a 6 level quantization. So, n is equal to 3 will get. Okay. So, from that we will get total 180 kilobits per second is the bit rate. Correct answer here is option D. Okay. This was a little bit twisted question, but try to do more and more type of questions which you find is difficult. Okay. Then it is easy. Correct answer is option D is the correct answer for your 6th question. Moving on to the 7th question. Let me just remove this to make some space. The 7th question is from tunnel diode. Tunnel diode has very fast operation in dash. It is actually asking the frequency range. A, gamma frequency region, B, ultraviolet frequency region, C, microwave frequency region, D, radio frequency region. Correct answer is C, microwave frequency region. So the tunnel diode is a type of semiconductor diode which works by tunneling effect of the electrons, right, in the microwave region or microwave frequency region. So the tunnel diode has a very fast operation in that microwave frequency region. So the correct answer is option C. Moving on to the 8th question. Bridge rectifier is an alternative for dash. Very, very simple question. A, full wave rectifier, B, peak rectifier, C, half wave, D, none. So we all know that bridge rectifier is actually connecting your load across the, like a bridge. Okay. So that is nothing but a full wave rectifier's version or an alternative. So it is option A is the correct answer. That is, bridge is actually a full wave rectifier's alternative. 9th question. A transistor has IC is equal to, it is a numerical question, okay. We'll do it. IC is equal to 100 milliampere. Then IB is equal to 0.5 milliampere. What is the value of alpha DC? So that is simply alpha DC or alpha. Alpha is a current gain. Okay. So first you should know that alpha is equal to, or alpha DC is equal to IC by IE. Right. We don't have IE, but we have IC and IB. Now from this, IE is equal to IC plus IB. Very simple relation for BJT or transistors. Emitter current is a sum of collector current and base current. So total sum is 100 plus 0.5, that is 100.5 milliampere. Both the values are in milliamperes. So IE is equal to 100.5 milliampere and you need alpha DC. So substitute IC by IE. Alpha DC is equal to IC is 100 by milliampere and milliampere cancel. Anyway, you can write it and then we'll cancel it out. 100.5 milliampere, cancelling this, and you will get 0.995 is the value for your alpha DC. Okay, so the correct answer here is option D. Moving on to the 10th question. You can see on board, which of the following is not a property of ideal op-amp? A lot of questions come in competitive examination from op-amp session, whether it is numerical or whether it is theory, especially from the CARA of op-amps. A lot of questions can come. Okay, so when you are preparing for any competitive examination for that matter of electronics, whether you belong to EEE branch or EI branch or EC branch, you should cover, there are certain topics which we cannot eliminate from any competitive examination, that is op-amp, Zener diode, BJT. These are very important, okay? Especially op-amp, a lot of questions can come. So here there is a theory question. Which of the following is not a property of ideal op-amp? A, zero input impedance, B, infinite bandwidth, C, infinite open loop gain, D, zero common mode gain, or infinite CMRR. Okay, so we all know that for an op-amp, input resistance is not zero. Input resistance is high or infinity. Okay, so that it should be able to eliminate the noise signals coming to the input side. Okay, output impedance is zero. Okay, so the correct answer here is option A, which is zero input impedance. It is not a characteristic of ideal op-amp. So the correct answer is for 10th question A. Again, we have done a video on op-amp discussing all the important configurations and CARA of ideal op-amp. So please do watch it. Okay, that is given in the analog electronics playlist. So these are the 10 questions which I have included in this video. So I really hope that you found this video useful. We have done almost 19 parts now for technical assistant mock test series. This is not meant for just any location but all locations. Okay, so if you found it useful, please do give it a thumbs up and share it maximum. And if you want more videos, please do subscribe to the channel. Thanks for watching and keep on watching.